This video is going to introduce thermochemistry, which is really just an analysis of how heat flows in and through systems, how certain processes generate heat, other processes absorb heat. We're primarily going to be looking at physical changes in this set of videos. In Chem 2, we go on to look more in depth about chemical processes and how they produce and or absorb heat. But let's dive in here with heat flow. And in order to do that, we're gonna recall from some earlier videos the difference between heat and temperature, because they are fundamentally different concepts. Heat is a form of energy that flows from high temperature to low temperature, or what we call down a temperature gradient. So heat will always flow spontaneously from a warm object to a cold object. In order to get heat to flow from cold to warm, you have to put energy into the system. And that's, for instance, how a refrigerator works. Temperature, on the other hand, is the average kinetic energy of particles in a sample of matter. It's a state property. You can measure temperature of a particular object at one moment in time, but heat can only be measured over time as it flows from warm to cold. And that the picture down there on the right is the other kind of I don't know, meaningful distinction between heat and temperature, because we can have two systems there if these are the same substances in those two beakers at the same temperature. But they will have different abilities to absorb heat. If you heat them both at the same rate for the same amount of time, one of them is going to be at a higher temperature than the other at the end of that time period, which shows you that even though two things can have the same temperature, they have different capacities for absorbing heat. As we start to consider heat moving into and out of different processes, we need to talk about where the heat is moving or where the heat is coming from, where it is going to. And that is primarily a definition kind of situation. It is an identification of systems and surroundings, and it is up to the experimenter to clearly distinguish what constitutes the system and what constitutes the surroundings. So here we have some chemical flask with some substance in it. And we might consider the system that we're investigating, the system that we're measuring, the substance inside the flask. In which case it might, if you were to heat that substance up, it would radiate heat to the flask, and the flask would be considered the surroundings. On the other hand, we could draw the boundaries to be everything not the flask and the contents, and we could define the system as the flask and the contents, in which case heat flow from the system to the surroundings would be from the flask out into the air around it, which gets to the idea of surroundings, right? Surroundings then are everything else. Once you define your system, your surroundings are all the other things that are not the system. So as we think about something like heating this flask up with some kind of a burner, then we're talking about heat flowing into this system. Note there will also be heat flowing out because as the glass gets warm, it's going to radiate heat to the surroundings. But under these circumstances, we would expect a net increase in temperature of the system because it's going to be absorbing more heat than it's losing. If you were to then take that burner away, well, now you're going to have a system that's hotter than its surroundings, and heat is going to flow from that flask to the surroundings, and then the temperature you would expect to drop. So that's defining kind of the system and the surroundings. And so what we want to do is we want to think about whether or not heat is coming into or out of a particular system. So again, a system then is all the important things that you're defining, that you are measuring. The surroundings then become everything else in the universe. And if that system is absorbing heat from the surroundings, or if it is losing heat from the surroundings, those are different processes. So anytime the system absorbs heat from the surroundings, we call that endothermic. And anytime it's losing heat to the surroundings, we're going to call that process exothermic. Endothermic processes are usually measured with positive heat, and exothermic processes usually with negative heat. There are three primary types of systems that we need to be aware of. That first diagram on the left is referred to as an open system, and this is where both matter and energy can move into and out of the system. So in this case, we have energy coming in the form of the heat lamp. That substance then looks like it's boiling, so it's going to produce vapor. That vapor is then going to go out of the flask into the atmosphere, and so you're going to lose matter through that vapor, so that's an open system. A closed system can have heat flowing into and out of it, but matter is contained. This is a nice little picture here in the middle, but this is certainly not a safe process. You should never heat any substance inside a closed container in any kind of a lab setting. We have, well, in any kind of a high school lab setting anyway. And then we have this last process, which is called an isolated system. In the isolated system, we have it contained in such a way that we're controlling all of the heat in the system so that there's no gain or loss. Typically, we'll want to run some kind of a isolated or near isolated system when there's a chemical process going on inside that flask. So we're not wanting to measure how much heat is generated in that process, so we need to contain it all so that we can measure it. A truly isolated system is impossible to create. Some heat loss will happen in any process, but we can get near isolated systems to make certain measurements. So those are our three types of systems: open, closed, and isolated.